I'm very excited to give a talk here. I'm going to talk about lower bounds for non-adaptive local computation algorithms. This is a joint work with Amir, Sohail, and Madhu. Okay. So let's start with the definition, like an informal one first off. So LCA are kind of interesting when we have like some problem that both the input and the output to our problem are very large. For example, here we are given like this large graph, and the goal is to only look at a small neighborhood or like a small hop neighborhood of a vertex and decide on the output of some problem for that vertex. That problem could be maybe graph coloring, that we want to decide on the color of vertices. And so the goal is, again, to look into this small subset of the vertices instead of looking at the whole graph. And also, we also want to output only a fraction of the output. We don't want to know about the whole output. Or another example is like maximum matching, where we can have the queries to be edges. And so then we want to have them, so we are queried some edge. We want to see if that edge comes in the maximum matching or not. Again, we don't care about the whole graph. We just want to make sure whether that edge is in the matching or not. And this is where local computation algorithm helps us. So more formally, this is what the algorithm does. We are given the graph and a prompt V. From then on, the algorithm can query any vertex U that it has its ID, and then it retrieves its adjacency list. For example, we start with vertex V, we get its neighbors, and then from then on, the algorithm decides on some other vertex, such as this one, and then it again retrieves its neighborhood, and so on. So this is how the algorithm actually can work. And so we want two things from our output. Yes?
But in this model, you mentioned that the inputs are large and that the algorithm does not have access to the whole input, right? So in that case, how would the algorithm be able to query, like, know the vertex U that needs to query if it does not have the full view of all the vertex?
So it has access to the IDs of the vertices, and so we can assume that we have the graph, but the algorithm can only access to local part of the graph, or like we have the query access to the graph, but we cannot see it like at once, all of it. Yeah. So we want the output of our algorithm to have two main properties. The first one is that we want it to be consistent, meaning that if we put together the outputs from different vertices, so they form a valid output of the problem. So for example, in the matching setting, we don't want to find out like edges that share a vertex. So that means that if we are querying, let's say we have two edges that share a vertex. If we are querying edge 1, we want to get, let's say, this is in the matching. And if we are querying edge 2, we want to for sure get that this is not in the matching. So if we put together all of the answers that are from our LCA, then we get a general output, like a global output. And another thing that we want is that the queries are the prompts that we can ask from the algorithm are not do not affect each other. They're history independent, meaning that if you ask for one edge and then ask for the other edge or the other way around, it's not going to change the output. So we don't care which one is going to be asked first. And again, we can think of this as we can think of as like having a global output, but we want to access to a local ones. And all of our local outputs come from this single global output. Yes?
I have a question about the algorithm. Technically, could you gradually query the entire graph, or you have restrictions on how many vertices you can query?
Yeah. We can think of as an LCA could technically do that, but the goal is to reduce this number. So we want to come up with algorithms that are efficient in that way that query the minimum amount that they can. Yeah.
And I guess you have limited memory.
Yeah, we can also think of that as well. Yeah, for example, I guess there are algorithms in coloring, LCA coloring, that they use poly delta log n, and they don't have to actually look into the n vertices. They only need to see something related to the degree. Okay, so now let's go into the non-adaptive LCA setting. So as I mentioned in the adaptive version, that is the definition of a general LCA is that when we were given a vertex, the algorithm could decide on the next vertex to get its neighborhood. But now we want to turn this into a non-adaptive algorithm where you cannot actually decide what to do after seeing a vertex. You have to decide on the algorithm before seeing anything. So that kind of translates into defining the structure of what you want to query beforehand. So before seeing anything, we want to define the structure of what algorithm would query. For example, that could be a tree that we want to query that tree and explore the neighborhood of our queried vertex with that tree. Okay, one example is we want to only take a random walk of length L and decide about the output. So this is one example. Another is a binary search tree that you would explore the graph in this way. Or also you can do something further exhaustive that would you can look at the whole R-hub neighborhood, and that would be a delta array tree of length R. So you can.
So just to be clear, the rooted tree is not necessarily a subgraph of the original graph, or is it supposed to be non-adaptive? You don't yet know its are?
Yeah, we don't know them. We just know the structure, and then as we run the algorithm, we see what vertices come up in the algorithm.
Okay, but the point is that you're not making queries as a function of what your previous queries.
Yes.
Okay.
Okay, so now let's see what we know about adaptive versus non-adaptive LCAs. First of all, there is this distributed model that we can actually use to get to the LCA model. So let me explain the distributed model. In this model, we have each node can send as much information as they want to their neighbors, and so each round is each vertex sending information to their neighbors, and they continue doing this. And the goal is to use as low as rounds as possible to be able to solve some problem. This is called the distributed model. Parnell's run reduction says that if we have an R-round distributed algorithm, then that would give us a non-adaptive LCA with delta to the R query complexity. So this is actually, so in the distributed setting, you can think of it as after R round, each vertex sees the whole R-hub neighborhood of, the whole R-hub neighborhood. Because at each round, they are seeing the information from their neighbors. At the second round, they would see the information from second hub neighborhood and so on. And so that means that if we define our structure tree for the non-adaptive LCA as a tree of depth R and degree delta, then this would be the same algorithm. This would give us the same, like each vertex would have the same information. Yes.
I guess I'm a little bit confused by what the non-adaptive model is here, because it seems like this reduction is imagining that like you know what edges are present and aren't present beforehand, and that you're saying that the tree you would take is literally just like a BFS tree in your R-hop neighborhood. But I don't understand how you know what tree to take if you don't yet know what edges are present in the graph. Is it that the queries are giving you like weights or something and not edges? Or?
I don't think they're giving us weights, but yeah, we don't know. So we can think of it as just fixing the delta to the R tree, and like we don't know what edges would be there and which one would not, but like this is a tree that we can fix, and then from there, if we know the maximum degree of the graph, so let's assume that we know the value of the maximum degree, then we can from then start at the root and then explore these delta to the R tree step by step, and we don't need to really know whether there is an edge. We just need to at each point be able to get the next edge.
I also was confused about this non-adaptive model. So like can go back to the example that you showed, like the binary tree.
This one?
Like like for example, U has degree more than 2. And then like how do you decide which 2 edges you explore?
Yeah, so you can think of it as like being random. So for each vertex, you would have access to a random edge at each point.
But then can't I just think of any adaptive algorithm also non-adaptively? Because it's just an algorithm, right? Like you specify each step what you do. Like in the first step, you query this one, and then you look at like 1 or 2 of the edges, and then you expand. So like I was just thinking, like can't you always model an algorithm once the algorithm is like well written? Can't you always define a structure to that algorithm, and then it becomes non-adaptive?
So in the adaptive setting, when you see a vertex, you can decide what to do next. So you might not want to continue from that vertex if you see it, like.
Yeah. So.
But here you don't have a choice. If you see it, you have to continue from it.
What are you deciding? Like you're making a decision based on the information that you have already collected. And how do you make that decision whether to go down that route? So
the structure of that tree in the non-adaptive setting, the structure of the tree is fixed beforehand, before seeing any vertices.
Yeah.
So you can just think of, like, for example, a random walk. You can just think of, okay, I'm started at some vertex. I want to get the next vertex at random, the next edge of that vertex at random, and then I continue doing that. And it does not, it cannot change the structure of the tree based on what we see.
Oh, I see. Okay, so I guess my question is, so the structure is kind of like a deterministic structure. There's no randomness in the structure.
In the structure, we can think of it as, no, there's no randomness. Yeah.
I think I understand it now. Can I just ask it, and you tell me if I'm right?
Okay. Yes.
So basically, like the idea in the non-adaptive settings for each vertex, you just fix a tree. That vertex is the root, and then your query pattern is like it's a tree that you don't yet necessarily know how it maps onto the graph. But then the way you decide how to make queries is you go to the root, and you're like, okay, in the tree, the root, maybe it has degree 2, so I'll pick 2 arbitrary or maybe random neighbors of this vertex in the actual graph and go to those, and then query each of them, and each of them will decide how many things they query based on how many children, I guess, they have in the root, and so on. Is that right? Okay, so it's like the way in which the tree maps onto the structure of the graph is sort of determined like adaptively, but the tree is just fixed beforehand.
Yeah, exactly. Okay. So now I'm just going to quickly go over this. So if you have an R-round distributed algorithm, then we can turn it into a delta to the R query complexity by taking the delta array tree, and this is the Parnas-round reduction. And so what we know about the non-adaptive LCA is that there is like a constant approximation for minimum vertex cover that runs in log delta over log log delta rounds in the distributed setting. That would imply a non-adaptive LCA with delta to the log delta over log log delta query complexity with the reduction that we just talked about. And but in the adaptive setting, there is like a huge gap here, where there is LCAs that can get a constant approximation of, again, like this problem, minimum vertex cover with polydelta queries. And this gap, as you can see, there is this gap that huge between adaptive and non-adaptive setting. And the question is whether this gap is necessary, or should we try to come up with algorithms in the non-adaptive LCA that do better? Yeah.
Yes, I don't know if I missed it, but in what setting will you be forced to do non-adaptive queries?
Do non-adaptive queries? Yeah, I'll just get into it. Yeah. So for why these non-adaptive LCAs actually matter. The first one is that so adaptivity has been studied in probability testing. So they do not use like they don't use it for like this problem that I mentioned with min vertex cover or so, but in some other problems that adaptivity comes up. And another usage of this could be MPC model, and where you are given, so the MPC model works in rounds, and if we had an adaptive algorithm, then for each adaptive decision, that would add on to the rounds of the MPC model. So if you have a non-adaptive LCA, that would really help with the MPC model. So what we prove is that if non-adaptive LCA were as efficient as adaptive ones, then we would get an improvement over the MPC model. That is, we would get from root log n to log log n into poly log log n for, I think, matching problem. Yeah. So this is another interesting things where non-adaptive LCA could be helpful. Okay, so let's get into our result. We proved that for maximum matching, maximal independence set, and minimum vertex cover, the Parnas-round reduction is optimal, meaning that there is a lower bound for constant approximation of these problems, these three problems, that says that we would require delta to the log delta over log log delta queries for non-adaptive LCAs. So this means that there is this inherent gap between adaptivity and non-adaptivity. So from here on, I will talk about the lower bound, and particularly for maximum matching problem. Okay, so let's overview what are the known, what do we know about like non-adaptive LCA if we want to think about it as lower bounds. So we have this Parnas-round reduction from our round distributed algorithm to the delta to the R query non-adaptive LCA. So if we want to prove a lower bound of delta to the R for non-adaptive LCA, that would imply an R lower bound for distributed setting. So that kind of tells us if you want to prove a lower bound for non-adaptive LCA, we should look into what lower bounds we know in the distributed setting and what techniques were used in distributed setting. So the first technique is round elimination. The way that round elimination works is that they prove an R-round algorithm. If you have an R-round algorithm for some problem PR, that would imply an R-1 round algorithm for an easier problem, we call it PR-1. And if you continue this, you'd get to a 0 round algorithm for P0 that should be trivial, but it's not. It's a non-trivial, but so that gives a contradiction, and this is the way that they prove the lower bound in distributed setting. But in the non-adaptive LCA, we don't have rounds, so we don't know how to use round elimination in a non-adaptive LCA. The second method is the following. So they would construct two identical, they would construct a graph where they have actually two vertices that produce different outputs, but they have isomorphic R-hop neighborhoods. So for example, one of these V and U, would one of them, they are producing different outputs to our problem, but these two graphs that we would see, they would be isomorphic. And so if our distributed algorithm would see any of these two, we cannot decide between these two outputs to be different. And so that way they can prove the lower bound. So there is, this technique has been used, for example, in the work of KMW, and they proved that delta over log delta lower bound for the distributed setting for approximate maximum matching. But there is, again, something here that is missing for non-adaptive LCA. That is that if our non-adaptive LCA was, let's say, a random walk, that for our setting, this random walk could be of length delta to the R because of the reduction. So we need something more than isomorphic R-hop neighborhood. We need to prove that there are no paths of length delta to the R that could help us distinguish between U and V. So in order to prove the lower bound, we need something stronger. Okay. So let me go over the techniques that we use. We are going to combine two techniques, one from distributed lower bound and one from sublinear time lower bounds. So first of all, we are going to build on top of the distributed construction of KMW. But from then on, we are going to use the recipe of BRR that has these two main steps. The first one is to change the construction so that there are no cycles. So the problem with cycles is that if you see a vertex twice, you kind of get more information about that vertex. So we want to just make sure that we cannot distinguish between vertices. So that and this is just going to help us prove the next step easier. The next step is to couple paths with they would have the same degree sequence. So what we want to do is to take any two paths of length delta to the R. We want to couple any this kind of path that would distinguish when we are starting at V and U, and prove that our coupling succeeds with high probability. And so then we can say that, okay, with high probability, we cannot find these paths, and therefore we cannot distinguish between V and U. Again, we are using V and U that has different outputs, but instead of having an isomorphic neighborhood of them, we need to be able to couple any two paths, have a coupling between the path of these two vertices.
And when you say coupling, you mean like literally like statistical coupling, where I'm imagining that like for whatever the fixed randomness that I use, you could explore, I'll imagine it explores this path for V and this path for U.
Yes, exactly. Yeah. So our main challenge here is that we have the recipe of the BRR paper, but what is missing is that we need to prove the coupling for each instance individually. So if we are given a new structure, we need to prove the coupling from beginnings. Like everything is just proof for a single structure. And so we need to, so this is the main challenge that we are going to get into. That is, we have to prove this coupling for the specific construction of KMW. Okay, so now we are going to get into the construction a little bit. So the construction is as follows. There are like these clusters that contain vertices. C0 is the cluster with the most vertices. And as we go further down this tree, each cluster is going to have a delta fraction of the vertices in C0 and so on. So the clusters are getting smaller and smaller. Another thing is that any two clusters that have an edge, they're actually a bipartite graph. And their degree is, for example, here delta 3 means that there is delta to 3 edges here, and there is delta to the 4 edges coming from here to here. So that this is a bipartite graph, and this side is smaller than this side. Another thing about this constructor is that all the color nodes have the same degree, but the white nodes have a smaller degree. So we constructed such as, if you look at this, for example, cluster node here, the degree of it would be sum of delta 0 to delta 3. So that the sum here is always the same thing for all of these colored clusters. Yeah. So this is what we need to know about the cluster. Let's also get to know about how they actually built this using induction. So there are two scenarios when we want to add to a cluster that is a non-leaf. For example, here C0 is a non-leaf. If you want to go from step R to step R plus 1, we will only add a leaf to it, and with the degree would be delta to the R. So if C is a non-leaf cluster, then it gets a child, only a child with label delta to the R. And if C is a leaf, then it would get, for example, here, again, delta this one. This turns into this one here, and it will get a lot of leaves. And we would label these leaves based on whatever the parent edge is, whatever edge it's missing, and we would label the rest of it so that the sum still remains the same throughout. And another definition that is important here is that whenever a cluster is born, we are going to color it with the step that it was born at. So if a cluster was born at iteration R, we are just going to color it with color R. So, for example, this is color 0, this is color 1, 2, and 3. This is also the definition of the colors that we don't need to say. Okay. So now let's get into how the construction of what are the two vertices that we talked about that have different outputs for maximum matching problem.
Okay. So there are no edges internal to a cluster?
No.
Okay, then I have a follow-up question. So you made this comment about making construction acyclic.
Yeah, maybe here. I think that was here. Yeah.
Okay.
Yeah. So we want to don't have any. For example, here when we have a bipartite graph, we don't want it to like.
Okay.
Yeah. I think that's the.
That's what you were going to say.
Yeah. Okay. So The construction that KMW ends up with is actually the following. So they would have this construction that we talked about, they copy it, and they would add an edge between each vertex and its copy. And now we want to find a large maximum matching in this setup. So the matching here is actually the edges between two copies because it has size n/2. And so we need, in order to answer this problem, we need to find these edges between the two constructions. And as I mentioned, the C0 is the largest cluster. So it actually turns out so our problem is actually finding these edges here that are between C0. So assume that there is like this algorithm that we are trying to run, and we have queried vertex W. And so for this W, in order to find the matching edges, it should be able to decide between these edge here, WU, and this edge here, WV, in order to find the edge that comes in the maximum matching. And so what that means is that we need to be able to distinguish between any vertex in C1, this cluster C1, and any vertex in this cluster C0. So this would be the goal. And what KMW prove is that R hub neighborhood of V and U is isomorphic. So they prove that if you look into the neighborhood of V and also U, you wouldn't be able to distinguish between VU. So this is how they prove the distributed lower bound. But in the non-adaptive LCA, the R hub neighborhood that is isomorphic is not enough for us, because if there is a path, for example here this path, that two paths, that one of them starts at U, one of them starts at V, and one of them ends up in a colored node, and the other one ends up in a white node, we know that their degree is different, so we would be able to distinguish between U and V. And this happens, so there are these paths that, and these paths are as low as like R+1 hub. Their length could be R+1. Like you don't have to actually have them very large. So what we want to prove from here on is that although these paths exist, but it's really hard for the algorithm to be able to find these. And so if you have like if you're given a random path, it would be really hard to actually get into one of them that is distinguishing between V and U. So first of all, let's get into our construction, that how we battle this. The first thing that we do is the following. So we add a set of dummy node to the construction of KMW. And if we do this, we add it such that a constant fraction of neighbors of each vertex is in this dummy node. And so we prove that if we have paths of length, let's say R log delta, then with high probability we'll end up at this dummy set. And from then on, we can assume that we can couple the path perfectly, because we will lose all the information about where we started. So if we end up at this set, we will lose the information of whether we started at C0 or C1, and so we would be able to couple perfectly from that. So the only thing remaining is the moderately long path, and this is our main challenge. So if we have like random walks so we figured out how we're going to get rid of path of length R. That was because of the isomorphism. Path of R log delta, more than R log delta, we had that dummy nodes. So it remains to prove that any path between R and R log delta can be distinguished with a really small probability. To do this, we quantify how close a path could be to revealing useful information. And we actually find a set of edges that if a path traverses those, then it would be closer to revealing information. And so if we could bound the number of these paths, then we would be able to bound the total probability. If you could bound the total number of these edges that we call identifiers, then we can bound the total probability. So it turns out that these identifiers are actually low-label edges. Let me define them. So if the index of an edge is less than its parent's color, then this is a low-label edge. And if the index is more than the parent color, it would be a high-label edge. And it turns out that the identifiers are the one that their label is less than their parent color. For example, here the color of this is 1, and the label here is 0, so this is a low-label edge. So our first observation is that the high-label edges, you don't need to read the whole claim here, but the observation is that the high-label edges, if you assume you have two clusters and they have the same edge, and both edges, the same label for their edges, and both edges are high-label, then the subtree of those clusters would be the same. So these have the same label, delta 2, yes, delta 2, and then they are both high-label edges, and these two are going to be identical. So the way that we prove this is actually by how we recursively constructed the structure. And the observation is that whenever a high label was added, the cluster was actually a non-leaf cluster when that was added. And this means that we need to only have the information about the label to be able to decide on what structure we are going to have after that vertex, after that cluster was revealed. So the information that we have to be able to construct the rest of it would be only on the label. And so we have like one step closer to proving this lemma. That is, okay, now we know high label edges are not going to help us because they have identical structures. And so it means that we need to now work with the low label ones. And if we were able to prove that, okay, the progress that each low label edge takes is actually bounded each step, then we would be able to come up with a lower bound, because the low label edges, the probability of their occurrence is also small because their degrees is small. So that would be helpful. So we prove exactly the thing that I just mentioned, that if a cluster has some, let's say cluster C has a child Ci, and this is a low label edge delta to the I, then its color is going to be increased by 1, by exactly 1. And the reason for this is that when low label edges are added, again, due to the construction and the induction steps that we take, the low label edges are added when the cluster C was a leaf. Then we were able to add a lot of leaves, and then that's the time that we add the low label edges. And so, and when we do this, the color just being increased by 1. And therefore, we have like a bound on how we can, how we are making progress by these clusters, by the color of these clusters. So we are ready to prove the lemma that says, okay, if you are taking these high label edges, you can assume that it goes and looks into the structure and comes up. If it does not come back to the same edge that it started with, it's not going to be a distinguishing path. But if it comes back, it always have to take a low label edge in order to make a progress. And we know that if an edge has label, let's say L, then the probability that we would go through this would be L over delta to the R, that is the maximum degree. And so we know that for each color, we need to take a low label edge of, that is delta to the, let's say the color is I, so we need to take a low label edge of delta to the I. And that probability is delta to the I over delta to the R. And if you put together all of the steps that we need to take for all of these colors, there are R colors. So if we multiply them, the probability of finding these paths would be delta to the 1, the sum of 1 to the R over delta to the R squared. And that is maximum delta, like the maximum degree over R. So over so 2D minus R, that is the total probability of finding these distinguishing paths. So now we were able to prove that, okay, the path can be coupled with this high probability. And that concludes the main things that I wanted to talk about. Just want to mention a couple of open problems. The first one is that, okay, what about other problems, such as vertex coloring, edge coloring for non-adaptive setting? And also we proved that the Parnas-Ron reduction was optimal for matching vertex color and MIS. Can we do better than this? Is there a problem that actually do better than the Parnas-Ron reduction? So is there a problem that breaks this reduction? Yeah, that's it. Thank you for listening.
Are there any other questions?
Okay, I know I asked this already, but the getting rid of cycles business, how exactly does that factor into this? Or I didn't see it happen.
Yeah.
And I also, I guess it's sort of like it screws up the coupling if you run into a cycle, because now you know that in one of the paths, two of the vertices are the same, so they're not really the same path as far as the coupling is concerned. Is this kind of the issue, I guess?
Yeah,
and then somehow you have to make sure that happens with very low probability, or I guess it doesn't happen ever.
Yeah.
If it's acyclic.
Yeah, so yeah, we make it acyclic so that it doesn't happen, and then the problem was exactly what you mentioned, that if there are two paths that are seeing cycles, then it would be really hard to couple them. And and the acyclicity argument, I think we would pick random bipartite graphs, and then we would argue that, I think the argument is kind of like that if we were to change the IDs for two vertices, then it wouldn't change. One of them has cycles and the other one doesn't have cycle, and so the probability of not having cycle would be still high. Yeah, I think it's kind of like this. Yeah.
I was just curious about the application that you mentioned to this massively parallel computing model. Is it the reason that you could in parallel explore the tree structure? If it's a non-adaptive non-adaptive algorithm that you already know the kind of tree structure in advance, then you can just assign different threads.
Sort of.
But in that case, they also need to coordinate. I suppose they need to coordinate. You cannot just.
Yeah, I think so. You would. Yeah,, that's also. Yeah, I think so. You would. Yeah, that's also. 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 Yeah, that's yeah, the coordination issue is also something there, but I'm not sure how I don't have it exactly in my mind that how we actually fix that, but we have the way that if using non-adaptive LCA in MPC model, we have a subsection of that in our paper as well if you're interested to look at it. But yeah, but the MPC model, the way that we have these machines that each of them has a small part of the input, and I think the main idea here is that if there is an adaptive one, then it has to go. At each round of adaptivity, we need to spend one round of knowing which one we want to query. But if it's non-adaptive, then each machine can do their own computation non-adaptively, and then send the information back. I think the main intuition is this, but yeah.
Can you do that? Because Alice was mentioning earlier that you have to query this node, and then it's kind of when you run the algorithm, it's still adaptive, dependent on the tree that you already have.
Like maybe you're saying that each machine might have some of the edges, and then if they don't have the edges, it's not adaptive, or they have to.
I guess I feel like each machine still has to wait for the other machines to finish all the work before this one.
Mm-hmm. Yeah, but I think if also we had an. So I think we can think of it as each machine is going to only answer the problem for themselves and then send back the information. Yeah, but I'm not sure exactly what you.
I'm just curious.
Yeah, that's a good question.
How different is the lower bounds for my vertex covered MIS? Is it the same construction?
I think the vertex, I think they're the same. For example, with small changes, for example, for us, we had to copy it so that there are matchings, but the base idea is the same.
Yeah, so I used to work with a group testing kind of problem where there is also separation between adaptive and non-adaptive.
Mm-hmm.
So I wonder if there is any way to interpret these kind of problems as coding theory or group testing problems, so we can take some techniques from there. Because for example, in group testing, if we want to study non-adaptive algorithms, in the end we just try to design a code book and it will turn into some kind of additive combinatoric problem. But I don't know if here can we just try to interpret this problem as coding theory, try to design a code book with really large, across really large space, and try to have bounds of this on the rate of this code as the number of rounds.
Yeah, I'm not sure. I haven't thought about it, but also this is kind of a local view of the answer. We don't. Not sure if in group testing care about locality at all.
I think one node can be interpreted as the graph has n node.
Mm-hmm.
It might be similar to the problem in coding theory where a code word has n coordinates. And one round would be so it will be R round and n those, and it will be a R times N matrix that satisfies some property.
I see.
I don't know if there is any property.
Yeah, that would be very interesting.
Yeah, because I saw Madhu had the all time. Yeah, he's really coding theory exposed now. Maybe it was.
It's like Alma